Technology is leading a global race to develop a quantum computer and a quantum secure communications network.
The Centre for Quantum Computation and Communication Technology is headquartered here at the University of New South Wales in Sydney. We have 6 leading Australian universities, the Department of Defence, and we have 12 formal international partners, including companies like IBM, Toshiba and Xivex, and then leading universities in Europe, the US and Asia.
Uniting researchers across the world, the Centre seeks to create revolutionary new computing and communications technologies by exploiting the laws of quantum mechanics.
Quantum mechanics is the branch of physics that describes the very small in the world, and the surprising thing is how differently that behaves. So we're used to the idea that in the everyday world we can intuitively understand what will happen. You know, if you drop a glass, it'll fall. You know, if you punch a wall, your hand won't go through it. But at the level of the very small, like atoms and electrons, or even very dim light, the way things behave is quite different and really quite baffling. Quantum computing is a really great example of how these fundamental principles can be applied to technology.
The Centre's mission is to develop the science and technology of a global quantum information network, and that really means building ultra-fast quantum computation and ultra-secure quantum communication. We basically have 3 major programs. One is to develop a silicon quantum computer using electron spins as the quantum bit or qubit. The second one is to develop an optical quantum computer where we use photons of light as the qubit. Finally, we want to develop quantum communication in order to be able to develop absolutely secure communication, and there we've got to address the critical challenges of being able to extend the communication distance and make it very fast.
So what is a quantum computer?
What we're trying to do here is to make a new type of computer where the bits are not just normal transistors that switch on or off, but they're more complicated quantum mechanical system that can be on or off or both at the same time. That's what quantum mechanics allows you to do. You can make quantum superpositions. And the physical system that we have chosen to create these quantum bits is based on single electrons confined in a silicon nanostructure.
The first technology for us is really to make single atom devices for conventional computing and see if can you actually take Moore's law all the way down to the atomic level. So that has implications for industry now. Can you push these devices smaller and smaller? So that's the first thing. But obviously the thing we're really aiming for is to make a quantum computer, and there you're predicted to get this exponential speed up in computational power, and that's kind of like the holy grail of the field at the moment. Can you actually make it? Can you you've got the technology there. If you make it, does it work? Can you actually encode it and do a computation on it?
Building a single atom device is conceptually simple. However, it requires the ultimate in technological control. Researchers at the Centre for Quantum Computation and Communications Technology use scanning probe microscopes to control the placement of individual atoms into a silicon device. Having world-leading equipment and state-of-the-art clean rooms are absolutely pivotal to the research.
This facility has got super high resolution lithography, which is patterning structures on a small scale. And we combine that small patterning with expertise in making silicon devices.
The Centre merges outstanding capabilities in silicon quantum computing with those working in optical quantum computing.
The key advantages to optical quantum computing are that photons carry the quantum information very well without degrading it. They're also very mobile, so you can move the information around within the quantum computer easily. And also you can talk to classical databases easily, like use a laser to read out information from CDs and DVDs.
The collaboration in CQC2T is really helpful for us. It means that we're able to specialise in an area that we're particularly good at, but connect very closely with other people's expertise as well. So in building a long-distance quantum communication system, we need people who've got quantum memories, where light can be stored in a high fidelity state for a long time. So we can connect with people at ANU who are working in that kind of area. We also need people who are working on improving the way you can entangle photons together. And there are people at University of Queensland, the group of Andrew White, who's working on that particular area. And we also have our theory collaborators who are always coming up with new ideas and better explanations for what we're doing and helping us drive forward. So we need to work together as a team, each bringing our unique expertise, but in a way where we're planning together to make one big breakthrough at the end.
This is science challenging the fundamental boundaries of human knowledge. However, there are immediate applications in areas such as data security. One of the centre partners is a Canberra-based company, Quintessence Labs.
We're clearly seeing an escalation in the frequency and sophistication of cyber attacks. Just during the last 12 months, there have been a number of incidents targeted against some of the largest global corporations and indeed against several government agencies. A recent report has highlighted that in the coming decades there could be a significant erosion in the international competitiveness of developed nations through the leakage of valuable IP.
So if we're successful, we have the potential to transform computational power and to basically create absolutely secure communication. And there are many applications of this. Decrypting and encrypting of information for data security, really fast database searching, and to take anything where there's a large number of variables, lots of information, and be able to simulate those systems.
We're looking towards building a quantum computer in the future, but here and now, what are the applications of this technology that we've developed?
The potential for this technology is immense. Currently Australia is leading this field internationally, and with the centre what we want to do is to maintain that lead into the future. We've got people coming from all over the world to work with us, and it's not really surprising because the research we're doing is exciting, it's demanding and it's challenging, and it's really at the forefront of research. It really is one of the greatest technological challenges of our time.
50 years ago, when the first transistor was developed, no one could have predicted the role that computers would play in our society today. As we transition to extremely small devices, we are now entering a new paradigm where quantum mechanics promises a similar technological disruption. We look forward to you joining us on our journey.